Hello, everyone. I hope that you enjoy yesterday evening with Yggdrasil after party. Today, I start presenting the things related mostly to big data and not strictly to Java, so be sorry about that if there is no so JVM-oriented stuff here. First of all, I'm a big data architect, so mostly working with designing system that works in scale and producing a lot of data and constructing these things. But also, I'm a trainer at Cloudera behalf of Compendium Educational Center. So if you want to see me teaching, also you can find me out. If you want to follow me, that's how I look from behind. And if you would like to do it more nowadays way, is Unilama on both communication channels. So what we'll talk about today? First of all, a little bit of the history, since columnar storage, columnar way of processing is not so fresh. About the rows and columns, how we can define them. Then a little bit of theory, related especially to the Google Dremel paper, then columnar storage and for the perspective of the file system, and then in memory, which is the fresh project. As I mentioned before, we have a long story after us with columnar storages. Usually in database systems, we have an array storage model that is classical way that you're storing element by the element. But in 1985, we have a quite important for a columnar storage perspective paper that covers the composition storage model. That could be right now told as base for everything that we know about that stuff. Based on that paper, the Netherlands company and with the support of the government created MonetDB in 1997 that actually is very interesting, but have no successful implementation in wide world. Then we have a recreation of this idea in this in environment of the software developers that we have in MIT C store, and additionally another version of MonetDB that is actually very well processing stuff. So Monet, of course, is one of the greatest artists, but I'll rather talk today about not the art, but the art of the programming. So MonetDB is our goal. First of all, is awarded database, actively developed. You can see it on the GitHub. Commits are every few days, so you can see how it's progressing. Actually, it's the mirror of this company, Monet Software Corporation, that presenting this stuff, and has no significant commercial success. But as you can see, can be compared to existing. This is quite old, but nothing changed more in that case. Based on the benchmark TPCH query first, as you can see, it's almost the same like hand-coded query. That means performing very nice. But of course, it's not a silver bullet for everything. First of all, what are rows? Rows are a continuous collection of column values. So we're storing, like in our Excel file, rows where all column values will be stored one after another, one after another, one after another. When we want to query this data, we need to read whole thing, then predicate, so filter out what we need actually, especially when we need only few columns. Also, when we need some specific rows, we need to evaluate on the whole data and then project. Of course, nowadays systems have some prediction models that in advance reading the data from the disk that actually works well fine. But what about the columns? So columns, when we store the values of the columns together, how can we see it on the picture? So we have two column files. First column, all data related to this column is grouped into one file. Then, when you want to read it, You don't need to read everything. You just hit it, especially this column, eventually run the predicates, so narrow down all these elements, all these rows that you need. So for example, can you treat it as an index, and then read the rest if you need. Especially important when you have very wide tables, a lot of the columns, and you usually querying 2 or 3 of them, especially in all-up cubes or something like that, when you're actually getting only one dimension. But columns are not for free. First of all, at the end, you need to recreate these rows, because all the application, how people are treating our data is usually recreating the rows from so the materialization of the row need to be done. And that is quite a common problem, and MongoDB right now is working hard to, as far as they can, postpone this process of rematerialization of this stuff. And of course, we have a very mature implementation of row formats. So they are actually very optimized in this way of reading, especially when the data is queried together, like 2 columns that are stored together, like summing 2 values, that the columns are in order. So this will be more efficiently working. And of course, there is an overhead of reading this columnar storage. So as I mentioned before, it's not the silver bullet for everything. Schema. To talk about the all memory layouts, storage layout, we need to define the schema. What is our data structure? Usually is JSON. Who likes JSON? Can you raise your hand? OK, that's good, because it will not be JSON in our case. But usually is represented as a JSON, but you don't need to think about it, because mostly operating on the models. And the key thing is a schema evolution, that somehow we need to preserve the whole history to not rewriting the previous data. So that key aspect is also covered by most of this columnar approach. So our example schema that we have an employee that have obviously name, have a position, have the previous employers that we have a name, department that works there, the location of this department, in which country, which street, and a postcode. As you can see, we can define the whole entity. Then we should define if its field is required. As you can see, there could be after the graduation guy that don't have a previous history of employment. So in that case, this group will not exist in our data. And as you see, we'll not only cover the flat data that we have, that we're treating our table, but also using this columnar schema, etc., we can somehow model, I'll unreveal that later, the tree structures. That means we can efficiently deal with that data. In the meantime, of course, software engineer versus software developer, you can choose and assign to both of sides. And then we can go to the first geeky stuff, which is Google Dremel. Based on this idea of the composition, the things into the columns, of course. Actually, the authors are admitting that they inspired by this idea, and the whole industry are talking a lot about it. This is actually the whole analytic system. So it's not only storage, but this is a key part of it. And the great benefit that they achieve is to use this columnar storage. And of course, the main goal of this project is to speed up the queries. Quite old, published this document in 2010. I will not read that name, but that happens at that time. And actually, Google has in production the system since 2006. That means, I don't know if you remember this Olympic Winter Games, but it's quite old. So, as I mentioned before, we have a tree of columns. So imagine that we have our table, that we have merging cells, that we can define many levels of it. Then we can easily create the paths for this column. So employer's name will be our definition where we are going. And we can also represent it as a tree. So we have an employee also required. This is actually that schema that I showed you before in the pseudo language, presented here as a tree. Different type of nodes here. This one required, this one repeated. That means that we can store there several items that have the same structure. And of course, there are some optional, because we can have this, or actually this name here is not so important for the company, so we don't want to know at which company our employee works previously. How we can store it? Actually, we need, besides of the data, of course, we need two variables. First is the definition level. This definition is taken directly from Dremel paper, probably not clear, and we have a repetition level that also is taken from the paper. As you can see, we have only two small numbers to describe where we have this data in schema structure. So maybe a little bit more verbose description of the definition level. So definition level is actually telling us on which level of the tree we have a null value, because some of the fields are optional, some are repeated, and repetition could be 0, of course. That means also optionality of the thing. So we can define small number based on the schema. So we knowing this in advance, because we're storing according to the schema, at which definition level we define this value. As you can see, first row don't have postcode because it's an optional. So we need to denote that, okay, on the second level, we have starts to be null. We don't have this information. This is very useful when you're recreating whole stuff. So to even more simplify the things, we can calculate from the schema the maximum definition level, and if we have definition level for specific column the same as the maximum, that means we have defined value. That's very simple. And of course, if we have a required field, that means we don't need that value because it always be defined. The second factor is the repetition level that gives us the information at which level we creating new element. So first of all, 0 means that all the time we're creating new, from the root level to the very, our value level, will create new thing. Here we have a 2 location for the specific department, so we creating on the second level, 0, 1, 2. We creating new thing. And based on that number, we also can determine the place on our directories, on our tree structure. Actually, the numbers that you have here are very slow and usually and always positive, so you don't need to consume whole integer field, so you can a little bit store with the less memory footprint or disk footprint from perspective of storage. Benefits of that: easy encoding and compression. Since we have all data in place, we can easily determine the maximum values, we can easily construct the dictionaries, we can easily use bit packing, etc. So that means we can better compress it, and using very simple methods instead of using very CPU consuming from perspective of the small object, more advanced compression methods. And of course, when we have all data related in one place, so when we query only one column, we get from one place. And of course, we're not storing the nulls because they are actually can be omitted, and based on the definition level, actually we know where the null is, so we don't need to store it. And the repetition and definition level knowns a priori before we, when we're defining the schema, very little numbers, so all the time is very well to store it in a very simple way. How? We'll see in the future. So someone before the presentation told me that without the cut presentation, it's not well rated, so at least I found out that we have a Parquet. Parquet as a floor, we're going from the storage, which is the basement of everything. So let's talk about the Apache Parquet. So we have an idea, which is Google Dremel. Yeah? So why not to code it in open source? Yeah? So we replicate things. Sounds familiar? Yeah, all the time we are getting the papers from the Google and recreating in open source world. So they actually take Day. What I mean Day? Day is a group of the people from the Cloudera and Twitter that wants to create some columnar storage. So first of all, they take literally Dremel structures and encode it in own way. The easiest way is to use thrift serialization. Do you know thrift? Can you raise your hands? Okay, thrift is a method of defining the serialization method. Then you can easily run it on many programming languages. That means it will be compatible between many programming languages and easy to recreate the serialized entities. All columns will be stored in one file. Of course, if you decide, you can put the data for a specific column to a separate file, but it is not required by the format. Implementation in C++ and Java. That means C++ is primary for many reasons, and thanks to that we have in C++, then we can use binding to any programming language that supports binding to the binary libraries, so shared objects. So that's why we can read Parquet file from very weird programming languages, starting with Ruby, Python, etc. Where Python is not so weird language. Of course, we have an overhead. This metadata, they're not here as an orange color, gives us a little bit overhead. Also, storing this is a little bit tricky because we need to collect of the data for a specific set of rows, then store it, since we don't storing records or rows only per column, but we storing whole rows. That means we need to collect a little bit and dump it on the disk. That actually, it's not so convenient because there is a possibility of losing the data when the memory buffer is lost, but this is the disadvantage of the whole thing. So I mentioned before about the bit packaging. So we have, when you have all related column values together, so easily you can calculate how is the maximum of that value. In this case, will be just 7 numbers here, yeah? And then if you're storing it as a regular, you need 32 bytes. If you have knowledge that you have only 8 possible values, you can use only 3 bits per each. That means, of course, this relation here a little bit weird that this bits going to the different bytes is made because we are using little endian. Of course, Parquet supports big endian, but really it's a very rare situation that you are using on nowadays systems. As you can see, using this simple trick, we can reduce 10 times actually the memory footprint, storage footprint. Probably for the 7 values, it's not worth it. But if you have thousands of the elements, probably it'll give you a big benefit on that. Delta encoding, another useful thing, because we have all information in place, we can encode some values into this very simple and not consuming a lot of memory way. So first of all, we're calculating deltas between the next elements. So 7 subtracted by 5 gives you -2. That gives you the first level. As you can see, we all the time having this minus. That is not so good because we need to use signed integer. That consumes a little bit more. So let's store only the minimum value of this delta, and then we have all positive values. So we need to store this information. So after we have this related delta, then we storing only the first value, the minimum delta, and then based on this related data, of course, packed as 2 bytes. As you can see, we have only 4 possible values because from 0 to 3 is only that number. And using only 2 bytes, you can encode this number of values. Especially is useful for timestamp, for example. If you're storing timestamps, these deltas will be all the time even 0, that also consumes less, because after this bit packing, also you can use another technique to compress the data even more and not giving a lot of footprint. Thanks to we have all this information about the type, about the number of the elements, everything in place. You have all the information needed to encode it very, very efficiently. And here is not so good. We have a 10 bytes versus 32 bytes, but it's growing rapidly when you have adding new values and based on your structure. Of course, in Parquet, you can define which kind of the encoding you want to use. Another one is dictionary encoding. When you have all possible values, like enumeration, you store it once, and then you're referring only to indexes. Then again, this will be limited number of the enumeration. That means you can efficiently apply bit packaging then. So that also is a very efficient way. And the last thing that you can apply, especially in Parquet, is selectivity of getting the block. So not reading all the information, but specific part. So first of all, Parquet supports predicate pushdown. That means the system that reads information passes to the file system format driver information how to read the data and omit specific blocks. There is a work in progress commit. Actually, 2 days ago was the last comment, probably will be merged in near future, that we can use Bloom filters. Do you know Bloom filters, what they are designed? So Bloom filters is a very efficient representation of the of your data that gives you information is possibly value stored in this block or definitely not. That means you have also a little bit false positives, and Bloom filters is a little very small overhead because you're storing as a bit positions in your integers. That means in a very efficient way, then you can predict and actually there's using the few false positives get the specific column or even specific portion of the column. That means if you want to find out all employees from California, you're not even reading the whole column to predict that. You're reading only the portion of this column. That's also important, but Intel is leading that change, so probably will be done in near future. And that means the system will be more efficient. But from my perspective, I'm using Parquet since 5 years probably. It's very, very efficient right now and will be more efficient in the near future. So actually very promising technology, not strictly related to the big data. You can store your or regular file system. We have a driver for every programming language. Okay, so we covered the basics. We covered the floor. Then we can go a little bit upper because we since a year ago the new project pops up. We don't have in open source world the representation of the data in memory. So do you recognize this element here? Yeah. This is the comparison how we go through the hardware from the very beginning of industry to right now, and we have probably 8 bytes here encoded. The possible storage here. So Apache Arrow, quite new project. Actually incubating still and providing a lot of feedback. First of all, strongly typed columnar layout in memory. That means all benefits that we have in Parquet, storing all this information together, that are able in memory also. The zero copy reads, that means from reading from different programming languages, you can reach the same memory because the data is immutable in Arrow, so you can easily query this from different programming languages. Starting from JVM implementation in Spark that will be released in near future is implemented, and you can use it in Python, C++, and the latest news that we have in JavaScript. So maybe we end up with the coding huge applications in JavaScript because everyone needs that in the space. Arrow also supports inter-process communication. That means you can send one message to another system, but storing in memory and then referencing only the memory address where to read. And behind the scenes, in case of the Parquet, we have a thrift serialization. Here, we have a Google flat buffers. So what the Google flat buffers are? Google, again, technology, but right now open source. They do not provide only the paper, but the whole technology, especially that they're using in Google for Games, the very crucial component of Google infrastructure that allows developers to start coding on games and the communication between them. This is actually the variant of the protocol buffers, very similar technology that we have with the thrift. So you're defining the schema, and then you can serialize from different programming languages the buffers. And the key part of this thing is the late materialization. That means you don't, if you want to read from the schema only one field, you don't need to deserialize, materialize the whole record. You just have a reference where to read this data, and you don't need to create a whole machinery. So there is no JSON deserializer that needs all this data. So if I need one thing, I need only one thing. So we have an example actually directly from Facebook, because Facebook also using it when you use today Facebook Messenger. So you have all information passed also using that stuff. So we have some, again, schema, in this case class, string as a name, friendship status, person, spouse, and list of the friends. So how it's stored? It's stored as a flat buffer. That means byte after byte. And then you're referencing only the offset when you want to start read. If you want to read only spouse here, so we have information only seeking to the information that our information will be stored at 12 offset, going directly, and you don't care what is stored here. You don't care if there is a name. You don't need to reserialize. You don't need to allocate the memory for that additional one to represent that stuff. You're only reading this person in representation. That speeds up a lot of the things. Especially at Facebook, they are using it to communicate between the layers in Android. That is, I'm not a very big specialist in the Android development, but they claim that is very efficient there. So example, how they are storing this stuff, again, in one place. As you can see, we end up with the series of the information that then could be easily encoded. All buffers in Arrow need to be, actually should be padded to 64 bytes, because it will be very useful for decoding this and utilize the modern CPUs. So as you can see, we need to store the information where we have a nulls. Then we need to store information where there are offsets. So it's easily, when we have this information to read, we're checking, OK, and the first element we have a null, not, we don't have. So we're going to our offsets, and to read this first element, we need to read actually from our values 0 to 3 bytes. So we're reading A, B, C. That actually is the same. If we have a null, or like in blue example, so we don't need to read it. But of course, for the format specific, we need to store this information. Of course, very well bit-packed here also. I know that is not so popular in the Java conference. The JVM is not the whole world. We have a lot of very good elements in our environment, especially in big data, that, for example, there are Pi, Num, and Pandas. Of course, not that Pandas, but the project that we have in Python community that handle very well numeric calculations. And there is a lot of things implemented already, so you don't need to actually reinvent the wheel. The same with user-defined functions. If you have a very skilled Python developer, why not use their skills? Probably has a good knowledge about your domain, so why not use knowledge about the thing? And the previous problem was, especially with the Spark, if you're using PySpark, so loading the data from the Scala, then operating in the Python. That means you need to somehow deserialize the data, serialize again in Python. That consumes the time and the memory overhead. That with the Arrow will be possible to read this data once and then operate with the Python and then back communicate. That creates very great speed up for first benchmarks. And from any programming languages, of course, not only from Python, but Python is very popular in that world. So performance, how this perform better? So GPU operation that can be done. Right now, they are highly working on that. So Schema located in the main memory, and with the CUDA, so the device will have our data and processing all the time. So it's also optimized that way. And also, why the 64-byte buffer? Because we can load it into the 512-bit wide register and utilize SIMD. What is a SIMD? Single input, multiple data. So your processor nowadays could do data parallelization. So process the data in parallel on the single unit. Of course, already implemented by Intel, AMD, Intel extension that actually Arrow utilize, especially that a lot of people from the committees of the Arrow committee is from Intel Corporation. So then, by one cycle of the processor, you can load all this data and do the prediction. That actually speeds up the process. So imagine when we have only one way and only one car lane here, and the rest of the highway is not used. And Arrow wants to utilize all these things. The takeaway from my presentation, data parallelization, that you can utilize the same stuff. Data layout matters, and so making the small optimization, you can achieve big things. You can use open source as a Lego bricks, so you can compose few things, maybe implement some paper if you really like. And actually, if you have every bit spared in the very specific place, you can reach the performance and reach the many things. And of course, few not obvious images from my side. If you want to play a little bit like this Hadoop here, we have a greenfield project. So if you're interested in big data, just approach me and we can talk about it later. And that's all from me. Thank you for your patience.
How huge is your typical data store for those solutions?
So several terabytes, up to 100 terabytes.
Can you please give examples of typical use cases when storage in columnar layout is beneficial?
Especially when you have a very wide table and you're using a very small subset of columns. If you, for example, have many dimensions of your cube, and then you're querying only few columns, then you're reading only these few columns, not the whole data. So if you have this very narrow table, like 7, 8 columns, so probably wouldn't be beneficial because already we have well-developed row formats. But if you have, for example, 30, 40 columns in your data, or the structures.
So typically my nodes should operate on different columns?
Yeah.
If I have different nodes, yeah?
Yeah.
Okay.
Another question, you mentioned that these guys are pretty much optimized on the storage level, but what about read-write operations? So for instance, I don't know, whether it's better when you have much more reads than writes, or vice versa in that sense. Could you comment on that?
So, of course, this Parquet and columnar is optimized from the reading perspective. For a storing perspective, slows down the thing because you need the buffer, you need to calculate these things, and also create the CPU intensive. But most of the workloads, you can really well parallelize the storing, of course, with some pitfalls, but then reading is very fast. And usually, from analytic systems, your end customers want to have the read fast, not write fast. But of course, this is the
sure.
pitfall.
So, and that means that as long as this is for analytic, it doesn't suit for mission critical storage because I can lose some data, right?
Yeah. Thanks.
One more little question. When you showed this layout for person with relationship, a kind of relationship with those pointers to offset to another person's, is it a way a data stored in Arrow, or is it a way a data serialized? Previous one, yeah, exactly this slide.
So this is actually used by the Arrow behind the scenes, this technology. And they are not using this reference a lot. They are storing on inline to compress the things. Because this is only the representation how they're using in Facebook, that they have very complicated structures. And in case of Arrow, they're utilizing only these buffers in that way. So this will be, when you have these indexes, that will be referenced here. And then continuous data will be over here. So actually, this is utilizing the flat buffers, not the flat buffers itself.
Okay.
If there is no other questions, so thank you, and maybe see you in the future.